Okay, this video is on equilibrium, and specifically translational equilibrium. And equilibrium occurs when the net force on an object is equal to zero. So in other words, there's no acceleration. The forces all add up to be zero, and the object is at rest. So here's a typical example. We have a mass of 43.8 kilograms. It's suspended by two wires. So the mass obviously has weight, so there is a force of gravity acting downwards, Fg, and that force of gravity is being supported by two tension forces, so Ft1 over here and Ft2 on this side. And the obvious question is, what is the magnitude of those two tension forces? Well, we know that since the object is at rest, the net force is zero. In other words, the sum of all of the forces acting on this object add up to be zero. So what we have is a very simple vector diagram where Ft1 plus Ft2 plus Fg get us back to where we started, right? In other words, we've added these three vectors and gotten back to zero. So the total sum of those three vectors is zero. So this is Ft1, Ft2, and the force of gravity, the weight. So we have a very simple vector diagram, and we know that Ft1 makes an angle of 55 degrees with the horizontal. So in other words, this angle here is 55. That means this angle has to be 35. Same thing, this angle over here is 43, making this angle 47. And a little bit more math tells me that the angle over here is 98. So I have a vector diagram where I know the length of this side because I know the mass, and I know all three angles in the triangle. So basically I can use now my sine law to determine the magnitude of these other two sides. So let's begin with Ft1. I know that sine of 47 over its opposite side, which is Ft1, equals sine of 98 over its opposite side, which is the weight, so 43.8 kilograms, times the acceleration due to gravity, 9.80 meters per second squared. So you can see we've written a formula where the only unknown is Ft1. And when we rearrange this, we find that Ft1 is 317 newtons. So we know the magnitude of this tension force. I could do the same thing for Ft2. The only thing that's going to change in the equation is that this angle becomes 35, because that's the opposite side to Ft2, the second tension force. Everything on this side is the same. It's still sine 98. And the weight of the object, 43.8 kilograms and 9.80 meters per second squared. So what we end up with is the second tension force is 249 newtons. Okay. So we've used basic vector analysis on our vector diagram here to determine the two unknowns. Okay. And what we're doing is using this condition, which is our condition for equilibrium, that the sum of the forces has to be equal to zero, to derive the vector diagram for us. Obviously, the situations can get more complicated than this. Sometimes if we have more than just three vectors, we're not going to be able to create a vector diagram, and we may need to break this condition for equilibrium up so that it's equal to the sum of the forces in the x direction are zero, and the sum of the forces in the y direction also have to be zero. Okay? these two laws are basically the same law, one broken up into x and y components. This one is just saying that add up all the vectors. So that's our basic method for solving these types of equilibrium questions. In the next video, we'll talk about rotational equilibrium.